I will begin with a word of prayer. So, Dearly Father, we thank you again for this class. I thank you for this semester that we've had and time we have to study your creation. Just pray that you'd be with us today, help us to understand a little bit more about how to solve the wave equation and maybe the Laplace's equation. And I just pray that you'd be with the students, help them to study well in the time that remains this semester, Lord. In your name I pray, Lord Jesus. Amen. All right, so let me set up the problem for us here. We want to solve the wave equation. So, wave equation, something like partial squared partial u partial t squared is equal to well, this is the velocity squared times that. I think that's the right units. Oh, no, my bad. I think this would be the velocity squared times partial squared u partial x squared. So you can derive this equation by looking at a string stretched out under tension. And if you study Newton's second law on a little segment of string, you can work out that this is the differential equation that it has to satisfy. And that takes me about 10 minutes that we don't have, so I won't do that. But if you're interested, email me. I can send you a link. Because I have done it in previous versions of the class. But we would like to solve this. And let's suppose that we're going to solve it on 0 less than or equal to x less than or equal to L, all right? And it's going to be subject, let's say u of 0 equals to u of L equals to 0, right? So we have in mind that the it has fixed endpoints, right? So this string is pinned down between x equal to 0 and x equals to L, all right? And so basically here's x equals to 0, here's x equals to L, and u, in this case, if you don't like u, we could use a y here. I kind of want to use y. That's too late, I already used u. But, you know, so there's a string that's between here, and it might look something like this, right? I don't know exactly what it looks like, but something like that, right? And this partial differential equation models how such a stretched string will oscillate, will wave as time goes on. Now, in order to make this problem meaningful, we have to start by explaining how the string is initially set up, right? So we need two things. We need the initial position and also the initial velocity, right? So let's see here. Oh man, I did it again. U is a function of two variables, right? So I have to say what? I have to say, let's say u of 0 comma t equals to 0 and u of L comma t equals to 0. And that's for what? For all time, all right? And we usually just start time at 0 and look at positive time just for the sake of making things pretty. Okay, so then, initial conditions. So these are the boundary conditions, of course, right? Initial conditions, position, let's say. So that would be u of x comma 0 equals to, let's say, f of x, and initial velocity, which will say partial u partial t x comma 0 equal to g of x. All right. So these are going to be given functions. So for a particular problem, we'd be given these. All right, so maybe at the end of this derivation, we'll make up a particular choice and see how that works out, okay? But I just want to set up the so-called blank template solution for you guys to start with. So the first order of business is to separate variables. So we do basically the same thing we did last time, separation of variables. So we're going to propose that u of x comma t can be written as a product of a function of just x and a function of just time t, right? So this is the product conjecture. You might ask a question like, so how generally does this hold? Like, what's the class of partial differential equations that can be solved by such a conjecture? What's the extent of this method you're showing me? The answer is I have no idea. And when I've tried to figure it out, I have not gotten anywhere particularly substantial. Like, it might be an open question. But again, I'm not a PDE theorist or anything, so I don't know that much. But so here, if we take the partial derivative of u with respect to x, right? What do we get? Get straight to the point. That gives us x prime times t, all right? And the second partial derivative with respect to x gives us x prime prime, and then t. Right? So these x primes indicate total derivatives with respect to x of the big X function. And then likewise, we can take the time derivatives, and similar thing happens there. Ut is x t prime. I gave you more details in this last time. I'm being a little bit more brief this time. If you have questions, just speak up. I'll write another line or two. So I take those derivatives and I plug them back into the differential equation, right? So take these and plug them up in there, and we get the following. This marker's trash. Oh man, that was really bad. Oh well. Don't tell anybody. Let's see here. So UTT gives us x t prime prime equal to v squared. The v is given. It's the speed. It's the speed of the wave. All right. And it ends up, when you go through the physical derivation, depending on the tension of the string. But I won't get into that here. I'll just say that there's a fixed constant speed for the spring. String. Okay, so then we got v squared x prime prime t, right? And then the way you use the separation of variables, the next step here is to divide by the product solution, and that will reveal something pretty neat. So if I divide by, let's see here, I'm actually going to put the v squared over there too. So I'm going to rewrite this as t prime prime, sorry, one more step. Divide by xt, divide this by xt, all right? And that will tell me that 1 over v squared t prime prime over t is equal to x prime prime over x. Now, as we discussed last class, we have a very interesting equation in front of us, right? Because, I don't know, maybe very interesting is too much of a stretch, but it's this right here, function of t, right? This over here, function of x alone. So the only way that can happen is if we're looking at a constant, right? And so for reasons of making a direct connection with my notes and the four propositions that give you nice results, we'll do this is equal to minus some constant, all right? We don't know what that constant is yet, but there has to be some constant. And the reason I'm making the constant minus here is so that once I do that, this becomes, x prime prime plus kx equals to 0. And the time equation has to solve t prime prime plus big K v squared big T equals to 0. So it's like what we did last time for the heat equation, but at the same time quite different, right? So like these are ODEs. So to solve this one PDE, we end up facing a pair of ODEs for the product solutions, right? But this time, the ODE for the time part of the solution is second order. Last time it was first order. We just found an exponential in time. This time we're going to find sines and cosines in time. OK, great. So what was the next thing we did, if you remember last class? Because, of course, once I say something, you have it memorized forever and ever. Amen. Thank you for being such good students. It's very reasonable on my part to assume that this is the way students are. So that's sarcasm. So if I have to say it, I guess it undoes it. But the point is, we have boundary conditions. So the next thing we did was we applied boundary conditions. All right. So the boundary conditions, as stated, they imply that x of 0 times t of t is equal to 0, and they also imply that x of L times t of t is equal to 0, and these would be for t greater than 0. Right? So I'm just plugging in the boundary conditions to the product solution. But since the time solution that we're looking for is non-trivial, we're trying to find non-trivial solutions, non-zero solutions to this problem. Well, it must be that these guys are separately 0, right? So we immediately find that, well, what we really need is that the boundary conditions for the spatial part of the solution, those must also actually solve the boundary conditions directly, just without any respect to time. Right? All right, so what are we up against? We're up against the boundary value problem. So we face x prime prime plus kx equals to 0 with x of 0 equal to x of L equal to 0. And if you study k equals to 0 and k less than 0, you find no solutions, no non-zero solutions. So all that is interesting is from k equal to beta squared, which is greater than 0. All right, so here I'm assuming that beta is greater than 0. I used gamma last class for this, but I can use beta now because I haven't foolishly used up beta in the definition of the partial differential equation like we did last time. I like to use beta for this. I don't know, it's just me. But so here's the deal. If that's the differential equation we're solving, well, you guys know how to solve it, right? X prime prime plus beta squared x equals to 0. What is the solution to this? What are the characteristic equation? It's what? Lambda squared plus beta squared equal to 0. So solutions to that are lambda plus or minus I beta, right? So anyway, getting to the point here, the solution has the form x equals to something like, a cosine beta x plus b sine beta x. Using the middle part of the course, right? The easiest part of the course, right? I think it's the easiest part. The constant coefficient problem, right? The good news is that's usually like 30% of the final. So that's the 30% you shouldn't lose any points on, right? Save all your points for like the power series problem, you know? You could try to get better, but that's a steeper hill to climb than getting better at this part, right? Okay, anyway, we have boundary conditions. So what do they have? So this, of course, is x of x. X of 0 is a times the cosine of 0, which is 1, plus b times the sine of 0, which is 0. So that being 0 tells me that a is equal to 0. So it looks like cosine solutions are out of the running, right? But if we look at x of L, which is going to give me, well, a was already 0, right? So it gives me b times the sine of beta L. That equals to 0. Well, we'd be in trouble if sine was never 0, but good news for us, sine's 0 infinitely many times. So we've got like infinitely many workarounds to that equation, you know? Anytime you've got beta L equal to what? How about n times pi? For n an integer, that's the solution there that allows for b to be non-zero. Now let me again mention that for n equals to 0, we get the 0 solution. And for negative values of n, we're just getting another copy of what we already have for positive values of n. So without loss of generality, just, you know, use n in the natural numbers. And so what we find is that our x sub n of x is got the form some constant, we'll call it b, and let's see here, what did we figure out? Beta is n pi over L, right? So we've got beta sub n sine of n pi x over L. And we went looking for one solution, and we just found infinitely many, so that's pretty awesome. That's why I'm adding the sub n to it, to indicate that there's an n dependence. I mean, just take a second to pause and talk about how profoundly weird this is relative to what we were doing earlier in the course. Earlier in the course, what did problems we solved look like? What's the difference between what we're doing right now and what we were doing in terms of this part of it? Before, we were solving stuff like x prime prime plus beta x equals to 0. Would say x of 0 equal to 1 and x prime of 0 equal to 2. That's earlier. What's the big difference between that and this? What's the difference between an initial value problem and a boundary value problem? Fundamentally, the difference is for an initial value problem, right? You're given two conditions at the same independent variable. We have existence and uniqueness theorems that say this can always be solved. It doesn't matter what the choice, like if I was to put a k here, it doesn't even matter what k is. I can solve that. And I will find a unique solution subject to those initial conditions. All right? I proved that this semester in another class, more or less. Up here, there are no non-zero solutions unless you are so fortunate that k is equal to beta squared, which apparently means n squared pi squared over L squared, right? So what I'm saying is, unless you're so fortunate as the value for the differential equation happens to be one of these very characteristic values, there just are no non-zero solutions. that is so very different than, it doesn't matter what the initial conditions are, you find a unique solution, right? Boundary value problems are far more demanding, right? They're much pickier as to whether or not there's actually an interesting solution. Nevertheless, we found that if you go and you allow yourself to, sort through all possible different differential equations of this form, we do get a whole infinite family of solutions like we just found. All right, so for every one of those family, we are faced with the temporal equation, the time solution equation, right? Which we got to solve what? So then t prime prime, how's it go? Plus what? Plus kv squared, but my k is n squared pi squared. So we've got n squared pi squared v squared over L squared t equals to 0. I don't know about you, but it doesn't give me great joy to keep writing n squared pi squared v squared over L squared. So in order to make this a much nicer looking equation, let's introduce yet another variable here. Let's call that omega. T prime prime plus omega squared, actually. T equals to 0. So here, omega is n pi v over L, which is, for us, greater than 0. We assumed that I said velocity, but I really mean speed. It's the speed of the wave, truth be told. All right? So then what? You can solve this, right? Solution's what? T of t equal to what? Something like C1 cosine omega t plus C2 sine omega t. I really should, technically speaking, I should put a little omega sub n on this. Let me start adorning these with n's, because there's an n dependence. And I guess this should be like a, well, these are just temporary. We're going to get rid of these in just a second, but I'll call this a sub n, and I'll call this over here b sub n. Actually, maybe we'll keep those, and we'll get rid of the b sub n. See, what I'm talking about here is when we put these together, and we look at the nth solution, right? We need to include some constants probably, but what I'm going to say is we could just write this. We've got a sub n cosine of omega n t sine of n pi x over L plus b sub n sine of omega nt sine of n pi x over L. You know what would make this equation easier to write? If we introduced yet another letter. Like you could call this k sub n times x, and you could call this here k sub n times x. You could introduce a k sub n equals to n pi x, n pi over L. I think this was usually called the wave number. That would save us some writing. But anyway, I'm not going to commit to that. I'm just saying you could do that. So we find one of these products. So what I did just now was I set the big B sub n equal to 1, right? Without loss of generality, set B sub n equals to 1. And then following Fourier's genius step, we don't just use one of these for our solution. You use an infinite series of these for our solution. And that forms the so-called blank template, as I call it. So we have, I'll write it up here. So we propose, I call it the blank template solution. That's not like an industry standard or anything. I just, for the sake of my course having language, I introduced that. So we've got u of xt equal to the sum n equals 1 to infinity of a sub n cosine of omega sub n t sine of, why not, knx plus b sub n times the sine of omega nt times the sine of kn. And of course, you could write just one sine and like factor it out if you wanted. Here, just to be clear, omega n is n pi, what was it? N pi v over L. And k is n pi over L, k sub n. So if you take a step back and close your eyes, find that nothing's really changed at all. Let's see here, 3141. Where was I? Yeah. So you'll notice that we have not yet used the initial position or initial velocity, right? So this whole setup works for any choice of initial position or velocity. Now, so we could make up one. All right, let's make it up. So suppose that u of x comma 0, my f of x as I've called it, is equal to, let's say, I don't know, 3 times the cosine of, I don't know, 7x plus 47 times the wait a minute, sine rather. My bad. Changing that from sine to cosine is the difference between not doing or doing a whole infinite set of integrals. So it's a much harder problem if I put cosine here. Let's not do that. Sine at the moment of, I don't know, 13x. Okay, that's enough, I think. We're going to use, we're going to set L equals to pi, and we're going to set V equals to, we're just going to leave, well, let's put V equals to like 6 for the sake of seeing how that works. Putting L equals to pi is nice because that makes this what? Just NV, right? Or in this case, 6n. And that makes this what? If L is equal to pi, this is just n, right? So it's probably in our interest to rewrite the blank template solution one more time, subject to my, my choices. So I just made these choices. Given. All right, these are given to us now at this stage in the game. So with those givens, my blank template solution looks like sum n equals 1 to infinity of a sub n cosine 6nt sine of nx plus b sub n sine of 6nt sine of nx. All right, great. So that's putting those into play. So you guys tell me, why is this problem that I've stated so far, all right? I haven't even told you the initial velocity yet. We'll make that up when we get there, okay? Don't worry, when I give you a problem, like in your homework or on the test, I do make up the initial conditions at the start of the problem. I'm just trying to focus our attention where it needs to be. So look at this. If I plug in 0, what do I get? plugging time 0, what happens? What's the sine of 0? 0. All we're left with is the first piece. Cosine of 0 is 1, right? So I get a sub n times the sine of nx. And that's equal to what? Well, it's equal to what's given up here. 3 sine of 7x plus 47 sine of 13x. All right? Now, if we had another course in differential equations, like when I was an undergraduate, I had 2 courses in differential equations. I had the analog of this course, but then I also had a second course which was just on partial differential equations and series solutions. And so in that course, you might have a couple weeks to just study the property of Fourier series and so forth, right? We don't have that much time in here, so I just have to kind of tell you what happens. But you can prove that Fourier series behave just like power series in the sense that if you've got this equal to that, you can just equate coefficients. You have linear independence of the sine nx functions as it happens. So what this tells me, this tells me this is an infinite set of equations. There's infinitely many there, one for each n. And there's no need to do the Fourier trick we did last time where we integrated both sides after we multiplied by a sine. Like, we don't even need to do that here because we can just equate coefficients. See, this tells me that a sub 7 equals to something, that a sub 13 is equal to something else, and a sub n is equal to 0 for n not equal to 7 or 13. So you guys fill in the blanks for me. What are they? I'm trying to make the case that you don't need to spend 2 weeks of your life studying the mathematical foundations of Fourier series. Don't let me down. What's that? 3? Yeah, I like that. And the other one? 47. Right, there we go. That's it. So you can then give the general solution then, our blank template solution. It's partially drawn now, let's say. And we've got 3 cosine of what? Sine of what? Oh, I can't just do that. I've got the infinitely many b sub n's. I'm getting ahead of myself here. Oi. All right. Okay, so now we know that most of the a sub n's are non-zero, but there's one other thing I need to do. So what is partial u, partial t equal to? Can you take the partial derivative of this with respect to time, t? What do you get? We get minus 6 n a sub n sine of 6nt sine of nx plus 6n b sub n cosine of 6nt sine of nx. Now we already know that most of those a sub n's are non-zero, right? Great. So now I need to make up the initial velocity, and I'm going to be very boring for that. We're gonna also be given that partial u. What's the most boring thing you can do? How about it's initially at rest? So the string is plucked in this shape, but it's not given any initial velocity. All right, it's static. It's let go from this, and so that would mean that partial u, partial t at x comma times 0 is just 0. All right. So if we do that, that's kind of the easiest initial velocity that we can think of. Right? If that's the case, what does that mean about this? let's see here. When we plug time 0 in, this piece is gone, right? Because sine of 0 is 0. But we're just left with this piece over here. And what do we get there? Actually, I might not be able to do this. I'm about to find out I made up an impossible problem, I think. B sub n, that can happen. Cosine of 0 is what? Yeah. Sine of nx. Sorry, question marks. Oh, the one in your homework is more interesting. Rats. See, I'm a little. I mean, I guess I could just do the math and then. So usually, what happens when I try to avoid doing the math and I try to like be physically reasonable about things is I talk myself out of like clear mathematics because I'm simplifying the physics too stupidly, and then like 5 minutes later, I'll be like, oh, I should have just done the math. So let's just do the math and accept it. Hopefully, it works. So if this is equal to 0, what's that say about my b sub n's? This isn't hard. B sub n equal to what? 0. All right, great. So then the solution is simply this. Where was I? So we found a sub 7 was 3. So I've got 3 cosine of seven times 6 is what? What do you know? 42t. And then we've got a sine. N equals to 7, so 7x plus 47. So what's 13? N equals 13. 13 times 6. All right, I'll allow it. Cosine of 78t. Right? And then you got your sine of 13x. And that is the solution to the wave equation. We end up not actually having to do the Fourier integrals like we did last time because the initial condition's already a Fourier sum. Like if you're given Fourier series as your initial position and initial velocity, then you don't actually have to reformulate them as the Fourier series, right? Because they're already the right format. It's when this is not in the right format that you have to go back and use the Fourier theorems to like rewrite it as a sum of sines. That was what your homework problem is more like that. So anyway, that's. So what can happen here, guys, is if my initial velocity was not 0, but suppose it had like there are things I could do here which I guess would be physically unreasonable. I think. Maybe not. But if I had put a, like, let's think through this for a second. If I had put a term which was, you know, like if I put like a, maybe a sine of 7x here instead, right? If you can imagine this have been sine of 7x, for instance, as an alternate reality to this example, then that would put a sine of 7x here, right? And then you'd get b sub n equal to 0, except what? B sub 7 times 42 would be equal to what? There's a 1 next to that. So it'd be equal to 1. So you'd pick up like a one non-trivial b sub n term. So you'd pick up like one of these kind of terms in the solution, right? So that kind of thing can happen. There's generally going to be some kind of interplay between the a sub n's and the b sub n's for more interesting initial conditions here. But anyway, let me go on. So, oh man. The other remaining partial differential equation for us to solve in the 7 minutes of class we have left is the Laplace equation. But the good news is we can solve it in 7 minutes. Let's see how. So I'll do it on the sideboard for a second here. But the Laplace equation is partial squared u partial x squared plus partial squared u partial y squared equals to 0. We're just looking at Laplace's equation in the plane, all right? And so for this guy, you let your solution u of x, y, no time this time, all right? So you got your x of x and your y of y, right? That would be my product solution. And take derivatives. Uxx is what? Well, it's x prime prime y. And uyy, it's xy prime prime. So if I plug that in to the differential equation, what do I get? I get x prime prime y plus xy prime prime equal to 0. But I suggest that what we do is rewrite this, putting, let's divide this by xy, all right? And that will give me x prime prime over x is equal to minus y prime prime over y. So this time, it ends up being the case, again, this is function of x. This is just function of y. So this tells me that it's equal to a constant, right? And I'll put minus the constant for the same reasons I've done before. But you could either plus, minus, whatever. But now we've got x prime prime plus kx equals to 0. And we've also got y prime prime minus k times y is equal to 0. So those are the ODEs that we face because of this given PDE. So like, if you're given boundary condition, and of course you can face different boundary conditions for this problem, right? But you notice what happens is that, for example, if we were given boundary conditions for x similar to the ones we just worked out, right? What would the story be? You'd get sines and cosines. Well, it could be not even sines and cosines. You get what? You get sines. An infinite family of sine solutions for the x if we had boundary conditions like we just worked out, right? But if that's the case, that would mean that the k is positive, right? Which would mean, what about the y? You wouldn't be having sines and cosines. You'd have what? What happens when you've got a negative, you got y prime prime minus something times y equals to 0. That has solutions of hyperbolic sine and hyperbolic cosine. So you get this pairing of cosh and sinh with hyperbolic sines and cosines. Let's see if I can find this thing here. Please tell me I haven't shut them down. No. Arr. Uh-oh. Well. Aha. Here we go. So, okay. So like this is a relatively simple problem, I think, because in this context, let's see here. So this one, we have the boundary conditions are partial u partial x is 0 at both 0, x equal to 0 and x equals to pi for arbitrary y. So what that ends up meaning is that for our x solution, we face like x prime of 0 and x prime of pi both being 0. When you look at my notes, that will force us into the case that x is a cosine solution, which is what I'm working out down here, right? So I have to, man, wait a minute, what? Oh, see, this is annoying. Look, I didn't put you see, this is going to be like exactly backwards from what I have over there. See why? Because I put a plus k here, whereas I got a minus one over here. So you have to flip the script on that to understand it. But anyway, choices of, come on. So anyway, after a bit, as I was saying, we get to see that the product solution for x is just cosine, right? And I end up studying y prime prime minus n squared, I think, y equal to 0 down here. And that has solutions of cosh and sinh of ny, all right? So then that's what I have for my solution to the boundary values. And then we put them all together to make this general blank template solution. It turns out that there's a piece from the 0 case in this one. And then after that point, I could fit values for a sub n and b sub n to fit the initial condition. Well, they're not really initial conditions here. There's just more boundary conditions in this case, but the other boundary conditions. And so I do that here, and after some algebra, a lot of algebra, some actually non-trivial algebra, I end up showing that, well, anyway, I end up with a solution. This one here is more exciting because this one has an arbitrary function for the boundary condition, but anyway, I hope I showed you enough that you can reason through the Laplace equation. It really is the same technique. It's just that there's no time, so there's no like initial condition thing. It's just there's a boundary condition, which is a simple one, and there's a boundary condition which you might need to use the Fourier technique to implement. But anyway, I'll see you guys Friday. So Friday we have lots of time to talk about like solutions to old tests and stuff and whatever else. So thanks, guys.